Welcome to This Explainer. Today, we're diving into something absolutely wild, the shockingly rapid and frankly terrifying evolution of the atomic bomb. We're going to focus specifically on the very first time nuclear weapons were discovered and the first time they were ever used. We'll trace this story from its start in purely abstract, theoretical physics, right up to its sudden and devastating real-world application in warfare.
So let's kick things off with a pretty profound question. How exactly did humanity go from just studying invisible particles in quiet university laboratories to detonating world-altering bombs in just over a decade? I mean, the speed of this transition is literally unparalleled in human history. Understanding exactly how we made that leap is so important.
All right, Section 1, Unlocking the Atom. We've got to start our race against time in 1930s Europe. Back then, scientists were simply trying to understand the fundamental building blocks of the universe. There were no thoughts of weapons of mass destruction, just pure scientific curiosity. But things snowballed fast. In 1932, James Chadwick discovered the neutron, using, believe it or not, a really simple device made with sealing wax. Just a year later, physicist Leo Szilard conceived the theoretical idea of a nuclear chain reaction, and by 1938, the actual splitting of the atom, fission, was achieved.
Now, what's fascinating is the very human element that sparked this whole revolution. In September 1933, Leo Szilard read a summary of a speech by the great physicist Ernest Rutherford. Rutherford had essentially mocked the idea of atomic energy, dismissing it as silly alcohol. Well, Szilard read that, got pretty annoyed, and while he was waiting to cross the street at Southampton Row in London, it suddenly hit him. He conceived the brilliant yet terrifying idea of a self-sustaining, neutron-driven nuclear chain reaction.
So Szilard had the theory, right? But the actual mechanism wasn't unlocked until December 1938 when Otto Hahn and Fritz Strassmann successfully bombarded uranium with slow neutrons and produced barium. They had literally broken the nucleus. During a long-distance phone call, Lise Meitner and her nephew Otto Fisch proved the math behind it, realizing this process released a massive 200 mega-electron volts of energy per atom. Frisch actually asked an American biologist what term they used when living cells divide, and he borrowed it to name this new phenomenon, nuclear fission.
Section 2, the Einstein-Szilard warning.
As global war loomed, that pure scientific curiosity we talked about suddenly shifted into urgent political panic. Szilard realized a horrifying truth. If a neutron-driven chain reaction was possible, so were atomic bombs of unimaginable destructive power. And with German scientists like Siegfried Flügge already publishing papers on exploiting nuclear energy in 1939, Szilard grew terrified that Nazi Germany might develop these weapons first. So an abstract physics puzzle instantly became an existential threat to the free world.
To sound the alarm, Szilard consulted with fellow Hungarian physicists Edward Teller and Eugene Wigner. They decided to draft a letter warning President Roosevelt, urging the United States to secure uranium ore and jumpstart its own nuclear program. But they needed a name that carried ultimate, undeniable authority. So they got the famous Albert Einstein to sign it. Hand-delivered to the president on August 2, 1939, this single letter changed the course of history forever.
Which brings us to Section 3, the Manhattan Project.
That warning letter did exactly what it was meant to do. It prompted a chain of political actions that culminated in the Manhattan Project, a massive, top-secret effort by the U.S. to build the bomb first. But to actually build a functioning weapon, scientists had to master a fast neutron chain reaction. They needed active materials, specifically uranium-235 or plutonium-239. When you bombard these specific atoms with neutrons, they eject more secondary neutrons than they absorb, creating unprecedented energy. And this all happens in just a fraction of a second.
Let's break down how this builds exponentially. A single fission event of U-235 releases roughly 2.2 secondary neutrons. In a perfectly ideal setup, one event triggers 2, which trigger 4, then 8, 16, and so on in a blinding geometric progression. Within just dozens of generations, taking place in literally microseconds, the energy release equates to thousands of tons of TNT.
But testing this theory? Oh man, it was incredibly dangerous. At Los Alamos, the actual Dragon experiment used this rudimentary guillotine-like setup. They would drop pieces of metal hydride through rings of the same material just to study these supercritical chain reactions. The renowned physicist Richard Feynman famously compared dropping materials through this equipment to tickling the tail of a sleeping dragon. One wrong move meant a lethal burst of radiation.
Moving into Section 4, the first nuclear explosions.
We have to take a somewhat somber pause here as we reach the climax of our timeline. This is where abstract theory becomes devastating reality. At 5:30 a.m. on July 16, 1945, out in the New Mexico desert, the Trinity test took place. The device, which they nicknamed the Gadget, was an implosion mechanism with a plutonium core. It exploded with a force of 18,600 tons of TNT. The heat was so unimaginably intense that it completely vaporized the steel shot tower it was resting on, creating a fireball that churned up the Earth itself.
Just 24 hours later, aerial photographs revealed this massive, radioactive crater. The extreme heat of the blast had actually melted the desert sand, fusing it into a highly radioactive, green, glassy substance. Humanity had literally harnessed the power of the stars and left an indelible, toxic scar on the Earth to prove it.
It's honestly staggering to look at the vast, terrifying leap humanity took in just a few short years. We went from the humble, almost makeshift laboratory origins of the Dragon experiment to the apocalyptic, real-world results being inspected here by Manhattan Project Director Robert Oppenheimer and General Leslie Groves. They're just standing there beside the twisted, pulverized remains of the tower footings at the Trinity crater.
Following the success of the Trinity test, two totally distinct weapon designs were rushed to the Pacific Theater for use against Japan. The first, nicknamed Little Boy, was a gun-type design. It literally fired pieces of uranium-235 into each other to create a critical mass. The second, Fat Man, used plutonium-239 in a highly complex implosion-type design. That one used explosives to compress the core from all sides simultaneously to prevent it from pre-detonating.
And then, these devices were used in warfare for the first, and to date, only time in history. On August 6, 1945, the B-29 bomber Enola Gay dropped Little Boy on the city of Hiroshima. 3 days later, on August 9, the B-29 Boxcar dropped Fat Man on Nagasaki. The immense toll of these explosions, which combine a massive concussive blast with lethal gamma radiation and subsequent firestorms, resulted in the tragic deaths of hundreds of thousands of people. Shortly after, on August 14, Japan surrendered, bringing World War II to a close.
As you reflect on everything we've covered in this explainer, I want to leave you with a final, provocative thought. The scientific leaps that started in the 1930s culminated in the events of 1945, ultimately ending a devastating global conflict. But they also introduced a terrifying new reality, a world where weapons so cheap, portable, and appallingly destructive actually exist. We figured out how to build them in a frantic race against time, but we are still navigating the immense, heavy responsibility of surviving alongside them today. Thank you so much for joining me.